What if I told you that the very fabric of reality, as we know it, is far stranger and more complex than we could ever imagine? In our quest to understand the universe, we've stumbled upon a realm where particles behave both as particles and as waves, where the act of observation changes the outcome, and where the very concept of a path is not well defined. Welcome to the world of quantum mechanics and the enigma of the double-slit experiment. Imagine this: a beam of light or a stream of particles aimed at a barrier with two narrow slits, with a detection screen placed behind. Classical physics would predict that if the particles were shot one at a time, they would pass through their respective slits and form two distinct lines on the screen. But reality, as it turns out, is not that straightforward. Instead of the predicted two lines, an interference pattern forms on the screen. This pattern, with its alternating light and dark bands, bears the hallmark of wave behavior. Here's the kicker: this happens even if the particles are sent through one at a time. The particles aren't merely passing through one slit or the other. They're behaving as though they're passing through both slits simultaneously, interfering with themselves and creating a pattern on the screen that can only be explained by wave-like behavior. This is wave-particle duality, a cornerstone of quantum mechanics. It tells us that particles and light exhibit properties of both particles and waves, depending on the circumstances. The double-slit experiment is a powerful demonstration of this duality, one that defies our everyday intuition and demands a new framework for understanding the microscopic world. But the mystery doesn't end there. The double-slit experiment also speaks to the probabilistic nature of quantum mechanics. Unlike classical mechanics, which predicts paths with certainty, quantum mechanics deals in probabilities. The particles don't have a well-defined path when they pass through the slits. Their behavior is governed by a wave function, a mathematical entity that describes the probability of finding a particle in a particular state. Bring a detector into the mix, one that can determine which slit each particle passes through, and the interference pattern vanishes. The simple act of observation seems to force the particle to abandon its wave-like nature and behave like a classical particle. This is a phenomenon known as wave function collapse. The double-slit experiment is a testament to the elegant strangeness of the quantum world. It challenges our preconceived notions and invites us to delve deeper into the mysteries of reality. Quantum mechanics, with its wave-particle duality and probabilistic nature, continues to intrigue us, and the double-slit experiment stands as one of its most captivating demonstrations.